thank you very much. Thank you all for waking up. Not all of you are East Coast jet lagged like I am, so it's difficult. So I'll talk about a paper that I put out fairly recently, and it's a little bit of an odd one because it's a result that I proved, and now there are 3 proofs, including one that's 15 years old. So you'll see that there's something to it, but there's also a little bit of a history. And so what I'll try to do is describe the nature of the problem, the result, and the history, and then I'll also give you some notion of a possible implication. And so to put this in perspective, the Robinson-Chenstedt-Knuth correspondence, which I imagine most people are familiar with, but I'll kind of review a little bit of it, is an important object in integral probability and algebraic combinatorics and in kind of the intersection of these. And going back to the late 90s, it was important in developing the first kind of universal, what are called Kadar-Prézy-Jang statistics, these sort of asymptotic results. Now, about 20 years later, there's a very nice paper of Devern, Orthman, and Virag, where they discovered or rediscovered a sort of invariance principle that says that if you look at last passage times and then you replace the weights by the image under the sort of semi-discrete RSK, which I'll describe, the result is invariant. And this was a starting point for the construction of an important object, which is called the Airy sheet. And this is embedded in something called the Airy line ensemble. So I'll give you a little bit of a picture of this. But the main focus of the talk will be on these 2 parts. One will be to describe a more combinatorial version of this result, a discrete geometric lifting. So I'll lift it up a little bit higher. And I'll explain a proof that I gave, kind of in the spirit of their proof, using what are called Pitman transforms. Now, I gave a practice version of this talk maybe a week and a half ago, and Konstantin Matveyev described to me a very nice inductive proof using Desano-Jacobi, which I'll explain as well, with his permission. And Duncan Devern also pointed out to me that essentially this result is in No-Me-Llamada, and I'll explain to you how that is the case as well. And it's embarrassing because I read this paper about 9 years ago when I first did work on this, and I guess the message is you only see what you want to see when you read a paper, and 9 years later you can see a little bit more. Okay, with that, then I'll turn to describing a few possible continuum limit questions, and this will relate to this Airy sheet, Airy line ensemble, but also a sort of KPZ equation version of it that really leverages this geometric picture, and this will be more open-ended. So somehow the message of the talk is 2-part. One is that sometimes it's very useful and illuminating to lift continuum results up to discrete level, and sometimes it's illuminating to then degenerate. And it's often hard to do both. And so we'll see how that plays out. OK, so what was the result that Devern, Othman, and Virag, I'll call DOV, wrote down in their work? So it's the following, and it takes just a drop to set up, but it's pictorially very easy. So you imagine that you have n functions, and these functions live on this sort of semi-discrete lattice. So fn lives on the bottom, fn minus 1, all the way up to f1. Okay? And we'll normalize them to be 0 at 0. We have some collection of starting points on the bottom and some collection of ending points on the top. And they're weakly ordered, the u's and the v's. Now we consider an ensemble of non-intersecting paths, pi 1 through pi k. K is arbitrary, that connect the u's to the v's. And we denote this sort of integral df circle pi to just be the sum of all of the increments of the f's along the horizontal components of these functions, pi 1 through pi k. So on each horizontal, you just take the little increment of the function at the level you're at, and you sum that over all the increments and over all of the pi's.
The increments are not positive necessarily.
No. The f's are completely arbitrary, so they could be negative, positive, whatever. Not even, I don't think they need to be continuous even, yeah. So then you can define what's called a last passage time. And I guess if you don't have continuity, then it probably should be something like a soup, just to be safe. But from U to V, denoted as this, which is just the maximum over all such ensembles of paths of this passage time. Okay? So this is one object, and you see this in the theorem. This is going to come up on both sides, in fact. Now, you would then describe what's called a or what I'll call a semi-discrete RSK shape, which is some sort of transformation on the set of the f's into this f tilde. And the way that it's facilitated is we say that the partial sum r equals 1 to L of f tilde Rx is equal to the passage time from the bottom left corner L times, so all points start at the bottom left corner. And of course, that really means that they start kind of staggered, one at the bottom, one up, one up. They kind of instantaneously separate. And they all go to position X at level 1. So it's almost, if you know these sort of watermelon type pictures, they spread out and then they come back together. Okay? And so the Lth term is essentially then the difference between this L sum and the L minus 1 sum. And this describes, this defines some sort of transformation, which, if you think about it, and we'll come back to this, is really a version of the RSK Q-tableaux as a function of x. So it's r equals 1 through n, and then as x varies, this is like the variation of the Q-tableaux. And what the identity that they proved said is that for any function f and any k and any starting points and any ending points, the last passage time through the f field is the same as the last passage time through the f tilde field. So you replace the f's by their image under this RSK, you get the same result. And this is a deterministic result. There's no probability here. Okay, so it's a nice, interesting result, and it has some implications that we'll come upon later.
Can you explain again, sorry?
Yep.
F tilde is obtained from f
through this transformation, which you should really think of as being like the shape of the tableau under RSK, which I'll describe in a different way in a moment. So this is, if you know Green's theorem, this gives a different interpretation of what the RSK shape is in terms of last passage times. And this is a continuum version of that, or a semi-discrete version of that.
Can you explain
Yep.
more of that?
Yeah, I'll come back to this. I'll come back to it in a more combinatorial and discrete setting, and so you'll see what that means there. Okay, but stop me if it gets confusing. So
I'm already confused.
fair enough. So stop me if it gets less confusing then. Okay. So this is the identity. But let me describe what it is in the discrete setup, and maybe this will be less confusing. Okay. So I also find it less confusing. So the discrete setup, so this is actually going to be a discrete setup, and this is what's called a geometric lifting. And what geometric lifting means is I take the max plus algebra semigroup, or semi-ring, whatever it's called, and I lift it up to plus multiplication. So everywhere that there was a max, I put a plus. Everywhere there was a sum, I put a product. And then you do the analogous thing with differences. So the functions, these f1 through fn, get replaced by some functions I'll call d1 through dn. And these are discrete functions, and they're described, they have a domain which is 1 through, let's say, infinity. It's, they're infinite functions. And we now normalize them at 0 to be multiplicative identity 1. Now, the way that you should think about these functions, kind of in the same spirit as these f's, is that they are partial products of vertex weights. So I can actually derive vertex weights by just taking ratios of dmx and dmx minus 1. So I think of the dm's as really the product of all of these vertex weights up to the position x.
So the m is the vertical axis?
M is the vertical axis, x is the horizontal axis. Yep. Okay, I have the same setup, some starting ending points, non-intersecting paths, except now these are lattice paths. So I need to go up and to the right. And I describe the analog of the last passage time, which is a partition function, which is just the sum over all paths of the product of the weights along that path. Okay. And now I describe, this is, again, the same sort of description of this geometric RSK shape, which is, except now, rather than starting off with all the points packed together, I need to start them off kind of staggered by 1. And so if L is 3, I start 3 points, one at position 1, 2, and 3, and then I end 3 points at position, I guess, x minus 2, x minus 1, and x. And this is what this notation with this sort of double bracket means. These are the numbers 1 through L. This is an L tuple of points. Okay, maybe it's not the best looking notation, but it represents just having an L tuple. And I do the same thing. I define this partial product of the D's tildes in terms of these passage times. So if I want to get the Lth term, I should look at the passage time for an L or the partition function for sort of L watermelon divided by the partition function for an L minus 1 watermelon. And that's what's going to give me my d tilde sub L of x. Okay? And x is representing the endpoint of the top right location.
So this last line completely determines the geometry.
So this completely determines. This is really, the analog of Green's theorem. In particular, if you were to replace products by sums and sums by maxes, this is the Green's theorem formulation of RSK correspondence. Okay? So this describes a transformation, except the only thing now is that the domain is not quite the same, because you see that when x is, say, equal to 1, I can only have a single path that goes straight up. If I had two paths, there's no way that the rightmost one could end up at position 1. So that means that I'm restricted that when L is equal to 2, then my domain on the d tilde needs to start off 1 over, because there's no way to pack two paths in and end up at position 1 on the right. So I get this sort of cutout domain, and this is the domain for my d tilde. So it's a little different already, because this was the domain for the d, and this is the domain for the d tilde. So the identity, again, says that partition functions are the same, except because the domains are different now, there's a little bit of fancy footwork in relating the two partition functions. And what happens is you look at the starting points, and you just lift them up until they hit the domain. So whereas here you started out on the d side at position 2 at level n, now you need to lift it up to position 2 at level 2. And the same holds true for position 4, and then anything past position 5 here will stay on the bottom. Okay, so the identity is then says that for any functions d, you have this relation between d and the d tilde partition function, where I've lifted the u's up in this manner, which is described in this picture. Now, this identity is obviously true, but actually by definition true, when the ui's, the starting points, are all packed to the left, because that was actually the definition of d tilde. Okay? So that, oh, sorry, when they're all packed to the left and when the v's are all packed to the right. So these are kind of the packed configuration is by definition an identity. And so the content of this is basically whenever the u's are spread out and the v's are spread out. Okay? So I want to describe 3 proof strategies for this result. But first, are there questions about the actual result? You know, does it make sense? Is it formulated clearly?
So on the right, you also take non-intersecting paths?
On the right, I also take non-intersecting path, except that now I start at these higher points, possibly.
And you said that if there was a 4 and a 5, then they would just be along the vertical row.
Yeah, so I think of my number system as being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that.
Can I go to the previous slide?
Yep.
Where is the definition of d tilde?
It's here. It's through these partial ratios. So,
Can you describe the right-hand side of that partial ratio?
Yeah. So when x, so I have my lattice, and I start my points off at 1 through L, and I end my points off at x minus L plus 1 through x. So I get some partition function, and I divide that by the same partition function, by you know, a partition function in the same environment, where I now start off with 1 fewer, and I end up, well, at the same x. So x, this would be whatever that is. And if I take the ratio of these partition functions, that defines for me d tilde, I guess in this case 3 of x. So it's a ratio of partition functions with 1 fewer, with the same left starting point and the same right ending point. Okay, so before I prove this identity or give you 3 proofs of the identity, let me just kind of put this into the context of different degenerations. How does this relate to DOV? How does this relate to other things? So the first thing is that if you can kind of think of this as living in 2 axes. So there's the discrete world and then what I'll call the semi-discrete world, where these functions are replaced by, but these discrete functions are replaced by continuous functions. And then there's the geometric or positive temperature world and then the 0 temperature world. And so this result sits here, and you can degenerate in either direction or diagonally. The diagonal degeneration is to this DOV work. So let's first take this horizontal, so from geometric RSK to RSK. And the idea there is that everything I've said holds true if I simply replace plus multiplication by max plus. So the formulation will hold true. These will be then differences here. This will be max, this will be a sum, so this becomes the last passage time. Same definition holds true here with the sum and the modified definition of partition function, the max plus version, and the identity holds true as well. And this is a statement then about just usual RSK correspondence. How does this sort of semi-discrete limit work? If I move down, well, there what you should imagine is you should, again, think of these D's as products of, kind of partial products. If you write that in exponential form, you can imagine taking, rather than having a product of lots of terms, dxm, if I write each one of these, I write it as instead e to the sum of, log of dxm's, then I can think of taking these as some partial sums for a function. And so in the end, I'll converge to a continuum sort of function e to the f. So my products will be replaced by exponentials. So I'm basically taking my lattice and I'm stretching it out really, 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 really long. So I have, or I guess compressing it maybe and keeping the space fixed. And so what I get there is this version of this positive temperature version of the DOV result, which defines passage times. So here I've put logarithms in, so it actually looks more additive. But I look over the simplex of possible passage, a possible path. So this is like my partition function of e to the passage time and the logarithm. And this is what I'm calling the sort of positive temperature or geometric version of this last passage time. It really is a partition function. And the same definition then of this geometric RSK, but in the continuum now. And the identity is then the same as this DOV. And if you imagine putting in a factor beta and then dividing by 1 over beta, take beta to infinity, this degenerates to this DOV result. Okay. Anyway, let me not focus on these and rather describe to you 3 proofs and perhaps in the course illuminate further these definitions of this identity. Okay, so the starting point, I gave you this formulation of the RSK correspondence in terms of passage times. And that wasn't actually the initial formulation, right? Robinson, Chenstedt, Knuth, there was they gave a, well, I guess Knuth in this case gave a bijection between integer matrices and pairs of semi-standard Young tableaux of equal shape. And what was understood as kind of obvious was that the top of the first row of that partition of the shape was the last passage time. And it wasn't until Green studied this that he realized that actually the lower level of the shape, lambda 2, lambda 3, lambda 4, also had meaning. And it had meaning exactly as these last passage times. So lambda 1 plus lambda 2 was equal to the maximal passage of 2 paths that were non-intersecting. Lambda 1 plus lambda 2 plus lambda 3 was that of 3 non-intersecting paths moving through the integer matrix. And so this, the definition I've been giving is really in the spirit of Green's theorem, but there are other definitions of RSK that are equivalent, and the one that perhaps is most familiar is the bumping algorithm. So one can give the bumping algorithm, in terms of operations, but there's actually a very nice formulation of it due, I think it goes to Neil O'Connell, using what's called Pitman transforms. So let me describe what this is. So this is going to be a map between 2 functions, so f and g, and they have the same domain. So the integer is bigger than or equal to r to the reals. You set by some convention. So this is in the usual RSK setting, and I'll describe what it means in the geometric setting as well. You normalize them to be 0 just to the left of their domain of definition. And now you define this g dot f and f cross g. And the g dot f has the same domain, and the f cross g has one smaller domain. It starts off at r plus 1. And the map is written here. It's not a very complicated thing. It's the function plus the sup of the differences staggered by 1, and this is the other function minus that same sup. Okay, so in particular, if you add the 2 together, these cancel, and you just get that the sum of these is equal to the sum of the f and the g. Now there's a nice pictorial description. So we're going to think of this Pitman transform as a map between a pair of functions fg and a new pair of functions where one of them has the same domain and one has a domain which is decreased by 1. Now what's the relation to RSK? Well, when you see RSK usually, you see it as inserting a word into another word. So maybe you would have, the word something like this, 1, 1. And now I'm going to insert into it some other word, 1, 2, 2, 3. Okay. Now, when you do the insertion, what happens is you get a new word, and you get something that bumped down. So it turns out that the word I'm going to insert is going to be related to this f, and what you're inserting into is the g. The new word that comes out is this f dot g, and f cross g, or sorry, g dot f, and f cross g is the thing that gets bumped down. And the way that it relates is the following. And once you write this down, it's easy to see it's the same. It takes a few moments, but I write the word I'm going to insert in word form. So it would be 1 to the 1, 2 to the 2, 3 to the 1. And I think of these as being, I map this to my function f by taking partial sums. So my function f takes values 1, 3, 4. So this is, well, and then maybe it keeps going. And from here, I've also formed partial sums of the number of 1s, number of 2s, number of 3s, like in a Gelfand-Zeltland pattern. So my function g would have entries 3, 5, 7, so forth. Or maybe just that's it. And if I then insert the word f into the word g, what I get out, if I again go back to partial sums, this one gives me the partial sums of the new word, of the updated word, and the f cross g gives me the partial sums of the bumped word. Okay. So this is just a rewriting of the bumping algorithm. Now, if you want to encode the entire RSK, then you encode it in terms of kind of a sequence of bumping. And the picture looks precisely like this. So you take your rows, dn through d1, and you start to insert one into the other. So you insert the dn minus 1 into the dn, and you get out, and you keep going through, and you eventually get your d1 tilde. And then you continue. And so each one of these lines just means that the function, the function gets propagated along the line, and then they get crossed together exactly according to this bumping algorithm. So this is describing a sort of recursive definition of the RSK transform using these Pitman transforms. Okay. And this is then nice because you can start to decompose and ask about the kind of microscopic behavior of each of these local operations. So the geometric version of this then is not so different to formulate, though I didn't really find it written anywhere, but you basically do the same sort of procedure, this max plus to plus multiplication. So differences became ratios, the max becomes a sum, and now you take the product of f with this and then g with the inverse of that. And this actually defines for you precisely the same transformation as from d to d tilde as this path formulation that I gave to you before. So this is a local version of this path. And there are various reasons why it's nice to have this local description. For instance, if you know that the d's are random and each one is independent of the others, this gives you a Markov chain. It tells you that this shape evolves as a Markov chain. And that is something that's important that we'll come back to a little later. But it also gives you kind of a more local way of proving results. So with this in mind, let me describe to you the first proof, which is to say maybe the second proof, because No-Me-Llamada was 15 years earlier, of this identity. So the approach which I take is similar to the approach in the zero temperature continuum world that DOV took. There are some nuances and differences, but the idea is to progressively build up a result by proving first for 2 layers and then moving from there. So the 2-layer version of the result, which means that I only have n equals 2, so 1 layer, 2 layer. When k equals 1, which means that there's only a single path, I move from one point to another point, this can be proved very much by hand. It's not a hard thing to just check once you know that that's what you should prove. There's a little bit of subtlety because you have this one cutout point. Going from going from one path to arbitrary number of paths is facilitated by a sort of decomposition, which allows you to split your domain into regions which are of kind of type 0, type 1, and type 2, where on each type you can then apply the step 1. So it's a sort of simple decomposition. It turns out actually you can also use, and I hadn't thought about this, but you can use Lingstrom-Gessel-Viennot to prove it as well. And the final step, which this picture makes look really horrible, and it is kind of a little horrible, is to do a decomposition of your passage time. So you're looking now for arbitrary levels. And what you really do is you prove a sequence of results, kind of for each level after you've done a replacement by one of these, you've applied some number of these transformations. You have some deformation of your domain, because each time you apply a replacement, it kind of lifts up a certain element of the domain. And what you need is a decomposition that splits your operations and singles out the effect of 2 consecutive levels. So you want to localize 2 levels to a single term so that then you can apply the step 2 result just to the one term on which you've localized, and everything else kind of gets transformed from d to d tilde just by the fact that you're not doing anything. So we want to apply our Pitman transform at a given level, so we do this localization of the problem, and we apply it at that level, and then we undo the decomposition. So this is the approach that I took. Now, when I gave this talk about a week and a half ago, and I gave a much sketchier version of the talk, Konstantin asked a question, which turned out to be a very insightful question, which is whether one could use another approach, basically Desano-Jacobi, and it turns out you can, and he provided me with a very nice proof, which I'll describe to you now. So this is a sort of inductive proof, so proof number 2 of the same identity. So we should think of the left and the right-hand side as in terms of matrices. And so what we do is we define a matrix MUV and then M tilde UV. I'm sorry, this should have a tilde, this D, otherwise it's not very interesting. So MUV describes for you the single path partition function from U on the bottom to V on the top. And M tilde UV describes the same thing but with the D tilde environment from position U to V, but where U lives on this sort of left and bottom area of the domain. Okay? So the identity we want to show is actually just that these MUV matrices and the M tilde UV are the same. Because then by Lingstrom-Gessel-Viennot, if I take minor determinants, that actually gives me the multipath partition functions. Okay. Now what is it that we know? Well, from the definition we know certain properties. So we know that if we, and again I'm using the notation here as a sort of double bracket is equal to the numbers 1 through k. So I know that if I start with a packed configuration to the left and then a packed configuration to the right at some other location, I know that the M and the M tilde are the same, and that was the definition of this geometric RSK. I also know certain positivity results. I know that as long as my right points are to the right of where I'm starting, my top points are to the right, I have positive weights because all of the entries of the D's are positive. And finally, and this last one takes a little bit of an argument, I know that if I start with all of my U's directly below my V's, and I go straight up and they're all packed together, then these are equal as well, because I can write these as ratios of the left justified identities. Okay? So I can just do this replacement, and so I have that identity of the M and the M tilde. Now the question is this enough? And so again, the goal is to now prove that kind of for any arbitrary starting packed configuration and any arbitrary packed configuration to the right, I have equality. Because once I know that, then I can just take k equals 1, and k equals 1 then just gives me identity of the matrix. Okay? So we know that this is true when I equals j and for all k, and we know this is true when I equals 1 and for all j and k. So this is some bits of information. And so then the induction is performed in lexicographic order on I, j plus k minus 1. And I'll describe what that means pictorially. So I is representing the leftmost, the bottom left corner, and j plus k minus 1 is the top right corner. Okay? So I'm going to first, I want to know that for any given I, that this holds true for all j plus k minus l's up to a certain level, and then I can go to one level beyond, and then I also am assuming that I know this for all smaller I. So if I want to show this for a particular I and then j plus k minus 1, Desano-Jacobi tells me that that partition function can be written in terms of this expression. So I can increase the number of particles, but then decrease my starting location, so decrease I by 1, and keep the ending location the same. And if I multiply that by just decreasing the number of particles by 1, keeping the starting location here and the ending location I shift by 1. And then I can add together the result of shifting everything over by 1. Let's see, I shift the top over by 1, and here I shift the bottom over by 1. And then I divide by shifting everything over by 1. Desano-Jacobi tells me that this is identity. And so the question is this good for the induction? And you can see that, in fact, it is, because either I'm shifting the left particle over by 1 or the top right particle over by 1 in each case. And so by induction, you get the identity holds true for all. Okay? So it's not a constructive proof, but it's an inductive proof. Now, the final proof is essentially in No-Me-Llamada. It takes maybe just a little bit of squinting to see it, but they give a matrix formulation of the essentially the geometric Pitman transform, or the RSK correspondence. And it was useful that they lifted to this geometric, this plus multiplication rule, because otherwise you don't really have this formulation. And so what they observed was that if I want to compute if I compute this Pitman transform from fg to g dot f and f cross g, then it actually solves a matrix equality. And what it does is it solves that I'll describe what these matrices H1 and H2 are, but I take some matrix which depends on the G times another matrix that depends on the F, and that should equal this H2 matrix depending on F cross G and H1 depending on G dot F.
Is it both H1 on the left?
Both H1 on the left. And that has to do with the fact that the domain is actually different between the left and the right. And so what do these H's mean? Well, the H's are transfer matrices or transition matrices for the following type of picture. So HR, I go from, so I imagine I'm applying it to a function which is defined from R on. And I think of my function as a partial product of e's, little e's, so ER plus 1, and so on. Now I put ER plus 1, ER plus 2 on each of these vertices, and everywhere to the left I have just a straight line. And so what I do now is I look at the transition probability, or the transition weight from the bottom to the top. So if I go from 1 I can only go up to 1. So actually I have a sort of diagonal section of size R minus 1 in the matrix, and then here I have an upper triangular section where I can go, say, from R to R plus 2, and I get a weight which is ER plus 1, ER plus 2. Okay, so that's a certain structure. And so these are what the H is. So H1 is actually, there's none of these identity terms. H2 has a single identity term, and so on. And if you think about what this product really means, this is really the n equals 2 version of the identity. Right? Because when I compose two of these, so when I take H1 times H1, what I'm really doing is I'm looking for the passage time in a rectangle, a 2 by whatever rectangle. And when I do the H2 and the H1, I'm looking at it with a little triangle cut out of the bottom because of this straight line. Because when I put together, so I have my,
It's like what you're doing is just a Yang vector equation, where you take these two rows, F and G, and you exchange them by using the Yang vector all the way around, and that turns into F times G and F and G dot F.
It has the feeling of that. Yeah, I don't know exactly how to write. Yeah, I don't know exactly how to write it that way, but I think that might be the case. Maybe there's a way of just seeing this as a degeneration of Yang-Baxter for some higher spin model or something like this. So when you and of course this is what the pictures are really suggesting, right? This sort of picture, it looks exactly like that, right? So the general version, of course, you can do this identity where you put R plus 1, R. And so what you find is that the matrix version, the encoding of this matrix, of this Pitman transform version of RSK is equivalent to this identity, which says just take H1 of the dn down to h1 of the d1, and then that's going to be equal to the hn of dn tilde down to h1 of d1 tilde. And now if you stare at what this means, this is the identity. This was the identity I wanted to prove, because the matrix elements here are precisely the partition functions, well, the single path partition functions of this left-hand side, and the matrix entries here are exactly the partition functions of this right-hand side. So this is why it really is embedded in No-Me-Llamada, and so this is, I think, actually the nicest proof. Okay, so all that said, let's now talk about, what's the purpose, or what sort of value do these identities give you? And the idea there, actually let me back up for a sec. So the idea there is the following. So people are interested, for various reasons, in understanding the nature of these passage times or these partition functions as you start and as you vary the starting and the ending points of your model, and in particular in the context of random weights, where these where these vertex weights are themselves random, and from the usual interpretation of RSK, you see that if you fix the starting point and vary the ending point, that's equivalent to looking at just the top row of this d tilde, the evolution of the d tilde sub 1. But with this identity, you see that you can actually encode the starting and ending point varying in terms of itself a variational problem or a partition function for the d tilde. Now, a priori, that might not be very good for taking limits, right? What you're interested in is really taking limits where both the number, not just the horizontal is going continuous, but the vertical, the number n is going to infinity. You want kind of a simultaneous limit. And if you think about it, in principle, as n goes to infinity, both problems could be really difficult. Solving a variational problem as n goes to infinity, getting any sort of handle on it is very hard. Now, it turns out that there is some very special structure when you take special choices of weights, which allows you to actually localize the variational problem on the side of the d tilde. And that structure has to do with, on the one hand, sort of Gibbsian line ensemble description of the image, and also a relation to, in the case of the zero temperature model, Shor processes. So let me just kind of describe a little bit of the structure and then how it's used, or at least why it's used. So this is a result. If you take the usual RSK correspondence and you push, rather than choosing just arbitrary d's, you choose the d's to be independent random walks with some geometric distribution. Well, it was actually understood, Neil O'Connell gave this particular description in terms of non-intersecting random walks, but Johansson knew this, and people knew this in algebraic combinatorics before this, in the sense of understanding proofs of the RSK of Cauchy-Littlewood identity using geometric random variables. But the idea is the following. So if these d1 through dn are independent random walks with some common geometric distribution, then the d tilde that you get out will be equivalent in distribution to n geometric random walks conditioned in a certain form to never intersect. So here's what the d tildes will look like. They will be separated, even though the d's are not necessarily sorted. The d tildes end up getting sorted so as they never intersect. And moreover, because of this sort of conditioned random walk, or actually there's a relation to Shor processes, they have the following very nice Gibbs property. So this is the domain of the d tilde. And now the d tildes are random because the d's were random. And the law of the d tilde is that of a Gibbs measure. So what it means is that if you condition on certain boundary points, and so I've written kind of all of the boundary points in black to this gray domain, though you see actually not all of them participate in this. The distribution, so conditioned on everything outside, the distribution of the points inside of this region, of the values of the d tilde inside of this region, only depend on these points that are connected in blue. And the only relations that are imposed are that they satisfy the correct interlacing condition. And so subject to that interlacing condition, you get a uniform distribution on the values, possible values of these open dots inside of the gray region. So this is, you can just kind of see kind of from the bijective approach of understanding RSK as a bijection, and then just seeing how the types are related to these geometric random variables. You also get from this that the d tilde is what's called a Schur process, and that actually gives you a way to extract finite dimensional distribution as n go to infinity. So if you take the number of levels to infinity and you go deep into this, you can extract certain asymptotic results. Now, in order to take a limit of the identity, remember the identity related the partition or the passage times in the zero temperature case of the d's to the d tildes. If you want to take a limit of that and get some sort of limiting passage time relating to something in the d tildes, you need more than just finite dimensional distribution convergence of the d tildes, and so you actually want that the d tildes have a process level convergence. And so the entire ensemble of d tildes, if you think of d1 and d2 and as a collection of functions, should have a limit. And so this is a method that Alan Hammond and I developed using the Gibbs property to establish this sort of regularity or tightness of an entire field, just given tightness of one point of it. And so here's what you get when you take the number of paths to infinity. Rather than 4 here, you take 100 or something like this. You see that your push forward of your geometric random variables, and this is a graphic from a paper of Deverne, Nika, and Virag. It creates this very nice ensemble of paths, and if you zoom in to the edge of it, you see that there is a limit, and this limit is known as the array line ensemble. And the Gibbs property that I was describing, this non-intersecting Gibbs property in the discrete world, becomes what's called a non-intersecting Brownian Gibbs property. So each one of these curves looks like a Brownian motion conditioned to stay above the curve below it and below the curve above it. And that's just the limit of the Gibbs property. Now, the whole point of this, this goes back in terms of finite dimensional distributions to Preffer and Spohn and Johansson, and then was strengthened to the kind of full convergence of the ensemble by Alan and myself. So the top curve, because it encodes the limit of this d1 tilde, which is the last passage time under RSK, so the top curve, which is known as the array 2 process, encodes what happens to the fluctuations of the last passage time from the origin, from a fixed starting point to a variable ending point. But this DOV identity, or the sort of discrete version of the DOV identity, tells us how to relate arbitrary starting points to arbitrary ending points if you do the same variational problem in this limiting ensemble. So we have, what we should really do if we want to kind of vary the starting and the ending point is we should look at varying the starting and the ending point in this picture and then ask about the variational problem here. And of course that seems hard as well. But what they showed was that actually the variational problem localizes to a variational problem at the edge. And so if you understand the edge limit, then you understand actually the behavior of this 2-parameter family of passage times. And so they were able to formulate, and there was a significant amount of work in doing that, this sort of 2-parameter limit, this fluctuation limit, in terms of the array line ensemble, in terms of a variational problem for the array line ensemble, kind of starting deep inside of it and ending at the top and looking at the consequence of varying those starting and ending points. So with this in mind, it brings to a question, which I haven't solved yet, but which is what can you do for the positive temperature, for the geometric version of this system? And so the first thing is to know, what is known there. Actually, let me remark that the DOV work relies heavily on the identity, which relates the d and the d tilde last passage times, the Gibbs property, but it also uses strongly determinantal tools, connections between the point process that you get by kind of slicing at a given time and certain random matrix type ensembles. So knowing the nature of like gaps and of this point process that you get at a given time. And that's something that we miss when we go to the positive temperature world. But we do have the Gibbs line ensemble property. So whereas for the geometric random variable usual RSK, we had this non-intersecting Gibbs property and Schur processes. In the case of well, okay, so there are two proofs that one uses there. One is a bijective proof, and one corresponds to what's called an intertwining of the tableau and the shape Markov kernel. So this is the idea that you keep kind of adding columns or adding rows, and you ask how does that evolve the tableau and how does that evolve the shape. And if you know from RSK that the tableau evolves as a Markov process as you add in a new independent random word, but you can show that for special choices of distribution, particularly geometric, the projection of that tableau onto its shape is also Markov. And the way you do that is through an intertwining of two Markov kernels. That goes back to the theory of Markov functions. Now there's an analog of that story in the geometric RSK setting as well. And the special distinguished choice of random weights are what are called inverse gamma weights. And so they take this particular form. So if the DXM, which are these kind of partial product terms in defining the capital D, if they take this form as independent random variables of this with this density, then the push forward, this D tilde, is what's called a Whittaker process, and it enjoys a softened version of the Gibbs property. So whereas before in the geometric setting I had non-intersecting geometric random walks, condition not to never intersect, here I have some random walks that can cross each other. The colors can kind of cross over each other, but they have some sort of energetic repulsion. And in terms of the Gibbs property, what it means is if I know the values outside of my domain, the values inside are determined by, well, they're no longer uniform, but they have an exponential or a sort of softened exponential interaction with their neighbors. So if you look at what is e to the minus e of something, it's some, it's some variant of a delta or of an indicator function, right? So it kind of looks some softened version of an indicator function. This is e to the minus x. So it's a softened version of this non-intersection condition that you get in this case. And so this was shown some years ago by intertwining and also by the bijective approach. And these Whittaker processes are, however, not determinantal, but we were still able with Bourdian and Reminick to prove one-point fluctuations of the edge. So if you look at the distribution of just a single point of the top curve, we could prove some limit as n goes to infinity as you look deep inside. And so the picture, which I think should be there, but I certainly haven't done, is the following, which is that you can ask what happens as you take a limit of the relation between d and d tilde in this geometric setting. And if you fill the d's with these multiplicative inverse gamma random walks, you can ask how does the behavior of say the log of the partition functions vary as you move the starting point and the ending point. And part of the picture is there. In particular, the limit of this line ensemble of this collection of the log d1 through d tilde 1 through d tilde n, if you look at the edge of it, we know that it converges to something that we termed with Alan Hammond the KPZ line ensemble. And there's actually a sort of continuum formulation of this in terms of partition functions moving through space-time white noise, which is kind of the natural limit as n goes to infinity of the definition of the d tilde. But the challenge, which I think is worthwhile, is to prove a limiting version of the invariance identity. And again, this really requires kind of localizing the identity to the edge of the ensemble and showing that stuff deep down doesn't really have much impact on it. And that's where it's tricky, because the stuff deep down needs to be controlled in some way, but we don't really have much control, at least presently, of more than just the top curve or the top few curves of this ensemble. The implication, if we could do this, is that this would tell us that this KPZ line ensemble, which was this kind of limit of the d tilde, actually encodes a sort of two-parameter version of the KPZ equation, which is describing the logarithm of these partition functions in the IID setting, where you start at some arbitrary point. So you started with a delta, it shouldn't be that. It should be the exponential of h starts with the delta function at position x, I guess, and ends at position y and evolves in between according to this KPZ equation. So this is some two-parameter version of KPZ equation where you couple to the same white noise, and it should be encoded in terms of the KPZ line ensemble. And so I think that that's a nice problem to work out. And there'll be some challenges. Okay, so let me kind of close now. So the kind of general and then specific take-home messages. So the generalities was, first of all, there was some value in finding discrete versions of the continuum properties. So when I saw this DLV identity, I thought it was quite interesting, surprising. Once you find a discrete version, and it takes some time to find it, then you see that there are some new tools that you can apply. For instance, this matrix formalism, this No-Me-Llamada approach, Lingstrom, Gessel, Viennot, Desino, Jacobi. Once you have a discrete identity, you can then take various continuous limits of it. And the truth is that sometimes neither of these things are particularly easy. So finding the right discrete version and then finding how to take these continuum limits. These can both be sometimes hard. So the specificities were that we looked at this discrete geometric RSK invariance. We showed 3 proofs of it. I would claim that mine is maybe the least illuminating of all 3. But for the semi-discrete RSK, which was the setting of this Doverne, Othman, Virag, this was the starting point for their construction of the Airy sheet from the Airy line ensemble. And I think an interesting problem is to do the same thing for the KPZ line ensemble and the KPZ sheet. In a sense, the whole purpose of this is that you transfer all of the challenges onto the line ensembles, onto these D tilde, onto these images under RSK, and all of the information of your probabilistic objects get encoded in that. And then we know a lot. In particular, we know that we have this Gibbs property, and the Gibbs property allows us to control a lot of regularity. So, for instance, it gives us tools to extract limits, or at least subsequential limits, and show that things have the right scaling. Anyway, so this is something that needs to be developed more, but hopefully this is a starting point. Okay, thank you very much.